So, if dy dx is very small, what does that mean physically? You always write absolute dy dx much more so than 1. It's taut. Okay? So, it's not perfectly horizontal, that's impossible. But there's a big difference between a cable that's slack, that hangs like this, right, versus one that maybe hangs like this. It's shallow, okay? What happens over here? The slope dy dx gets big at certain points. If it's very taut, then the slope doesn't vary too much from 0. It's a small number, okay? And the argument now goes like this. Well, if dy dx is very, very small compared to 1, then certainly dy dx squared is very small compared to 1, let's say negligible. And we neglect that thing, it becomes the square root of 1 plus 0, and the differential equation becomes y double prime equals w h. Okay? And that's the simple cable problem when it's very taut. Okay? And obviously you can integrate that if w is constant, okay, like just hanging on its own weight, and you made this assumption, I guess you get y would be a quadratic, like a parabola. And that certainly does look like a cable, roughly, if you look at it. Yeah, it looks kind of like a parabola. It's not the actual shape because we linearized by throwing away that term. Okay? So there's, any questions on this? Okay? I think it's just good to see it. Like I said, this is not, of course, mechanical engineering, but when I see things done in these books and they kind of, they misguide you, okay? They think basically that is the simplest of cables. How hard can it be? It's very hard, okay, when you include the fact that they have a nonlinear term. Okay? And this is something that's done quite a bit in analysis and engineering. When you have a problem that's nonlinear, the first thing people try to do is say, can I linearize it somehow? Because it's much easier, I think you would see, to solve this equation versus that equation. Sometimes you can do it with good assumptions, but there's always assumptions involved. Okay? Here, the physical assumption that allows you to go from here to here is that it's very taut, and hence it's a shallow arc that we're doing here. Okay, I'm on to this now. Since the book does it, let's do a simple electrical problem. You set up a differential equation for that. Okay, the idea of these, these problems like this is kind of a survey. I've got something from mechanics, dynamics, so for the first time with a particle. I know to the hanging tables, the structures problem. Okay, let's give the electrical engineering people something to talk about. Okay, this will be an inductor L. Okay, there's a battery with an EMF E, to be a function of time. And then you have a capacitor C. Okay, and then finally you got a resistor. I think I have to put down the symbols on, right? E of t is the voltage for the battery, it's a function of time. R is your resistance, which we assume to be constant. C is the capacitance of the capacitor, the farads, I guess, right? And L is the inductance, what's inductance? Henries. Okay? That's the inductance. These are all what's called linear circuit elements. Okay? Okay? You assume that L doesn't depend upon time or R, and of course in reality it does. When the thing heats up, the resistance actually changes. But it's supposed to keep this everything to be constant. So that's called the classical LRC circuit. Okay. Now, where's the differential equation come into being over here? Well, you have Kirchhoff's law. Okay? Where Kirchhoff's law says that when you traverse a circuit, when you traverse on the circuit, the sum of the voltage drops equals the sum of the voltage gains. Right? Because you're back to the same point again, so net voltage delta V is going to be 0. Okay. So, let's see what happens. When you go across the inductor, you get a drop of voltage L di dt. Okay, let me actually say basically I equals current. That would be an amps. And you also need a single Q for the charge on the capacitor. Charge. And you remember basically the definition is that Q dot would be Q to T is equal to I. That's the definition of current, right? You're seeing in the circuit how many coulombs of charge are passing in a given time. Okay. So across the inductor, we got a voltage drop of L di dt, plus, of course, the resistor, it's R times the current, by R. And of course, a capacitor, unfortunately, it doesn't involve the current, it's the charge over C equals the net voltage gain, which is E of T. Okay, so right-hand side is simple, it's just the voltage gain from the battery, and the left is the sum of all the voltage drops over the inductor, resistor, and the capacitor. Okay. Of course, I want to have a differential equation. Clearly, what's the independent variable over here? It's t. In the cable problem, the independent variable is x. Remember I told you have to get used to xt, okay? So in this physical problem, clearly the independent variable is time, which is t. What's the dependent variable? Looks like I have two of them. You got I and q. I don't want to have a differential equation that has two dependent variables in it. So I asked myself, is somehow q and I related? Yes. Okay, dq dt is equal to I. Okay? So in order to get rid of that q, I have to differentiate the equation. Okay? What I'm going to do basically is plug in for q, plug in for I dq dt. Okay, that's what we do. Different ways of doing it. But the current I as a function of time equals dq dt by definition. Okay? So what I'm going to do is every place I see I, replace it by dq dt. Okay? So I can get L. What's the I dt? That's the second derivative of q with respect to time. Right? Plus R times the current, that's just dq dt, plus 1 over the capacitance times q equals dE. That's my final equation, okay, in terms of the charge. Okay? So at t equal to 0, I have to know two things. I have to know q, the charge on the capacitor, I guess dq dt, or the current, right? And I can solve this differential equation, get a time history of q versus t. If I differentiate, usually people are interested in q versus interested in the current. And once I have the solution to the differential equation, I've got q as a function of t. I differentiate once, I got my current, and I can plot current versus time. Okay? And all the books do special cases. They do, they look at some of these, we've got everything in there. It becomes a little more complicated. Okay, it actually becomes like an oscillator because you've got a damping term. Okay? What's interesting is that if you look back at the equation that I derived for the particle with the aerodynamic drag, it's actually the same form as this. Okay? Both of them had t as the independent variable. Here, the dependent variable is the charge q in the capacitor. The problem I did with the particle going through the gravity field, instead of having q, you have s, which is the distance. And this is basically, in the old days, people did what's called analog computer models of things. What they would do is that in a lab, they could easily do this and build it and measure things, okay? And they'd actually take mechanical problems and make an analogy. Wait a minute, just like I told you. All you changes is the symbols. So you scale the thing, and then you predict the behavior of a particle going through a viscous fluid based upon measuring currents and voltages in the circuit. Okay? People don't do that anymore. Because we have digital computers and stuff like that. But in the old days, they did this analog type stuff all the time. Okay, so second order equation. Again, it's a differential equation. That's what the important thing is. Okay. Another one which we're going to look at is Newton's law of cooling. Okay. This is the most simplest of all models of bodies changing temperature. Okay. Very, very simple. Okay. It's variable. Okay. But I guess with certain things it works. Okay. Okay, so imagine the following, okay? I'm just going to draw some blob over here. Okay, some material. It has a temperature cap T of T. So T is equal to the temperature. Okay. And imagine it's immersed in some type of surrounding medium over here. Okay? Maybe it's a hot body, you just drop into some water, or again, for re-entry, you got something re-entering the atmosphere, like a space capsule, and it's heating up because of friction, but also because of heat convection, other stuff. And we'll say T sub A is the ambient temperature. So cap T, let me just do this a little more carefully. So cap T of T is the body temperature. That's a function of time, okay? So maybe, for example, you take like a hot cake out of an oven, it's very hot, you put it on the counter, okay, the ambient temperature in the room, is TA, and strictly speaking, TA should also be a function of time, right? You can't measure it, but for example, I took some hot object, and put it over here and had a very, very sensitive thermometer, actually the temperature in the room would change also. Okay, but it's so big. Let's assume basically that the space of this TA is so large that any change of temperature due to this hot body is negligible. So we call T sub A is the ambient temperature surrounding. We'll assume that that's going to be constant. This makes it a little simpler. Okay. Now what's going to happen? Obviously, there's going to be a heat transfer, between the body and the surrounding ambient fluid, whatever it may be. Okay? And the question is, how does that go? Okay? And one of the simplest models basically says that the time rate of change of the temperature of the body is proportional to this difference, T of T minus T sub T. And what happens now, this is where the book is very bad. It's written by a mathematician, not by an engineer. Okay? You can tell all the things that we take courses, trace the materials, these are positive numbers, right? Whenever you have an empirical constant, it's always positive, right? Thermal conductivity, it's a positive number, okay? And therefore, we're going to assume over here that we have thermal conductivity, which is the proportionality constant, and that it's positive. And the question is, what does the sign, SIGN, appropriate to this? So, I'm going to show you basically it's minus K times T minus T sub. K is constant. The book, okay, actually writes this KT minus TA, but K is negative. Now, that's crazy, right? No one tabulates material parameters that are with negative sign. Okay? Always positive. It's just a convention. Okay? So we're going to do that. Okay? Now, why do you choose a minus sign? Very simple. Consider the case where the body is very hot compared to TA. T is bigger than TA. What's going to happen? Well, if the body is hot, and I bring in a hot cake and I put it onto the table over here, it's going to cool down. So its time rate change is negative, right? It's going to cool down. Okay. So T is greater than TA, the quantity in parentheses is positive, and multiply by a positive constant, put a negative in front, it's negative. So it gives me the right sign. Conversely, okay, if I would take this body, let's say it's very cold, okay, take some ice, right, and put that onto the table, well, the ice is going to warm up, it's going to absorb heat. In that case, this derivative should be positive. And indeed that happens because you got a negative here, and now T is less than TA, negative times negative is constant. Okay? So this is called Newton's law of cooling. It's one of the earliest, simplest models to describe heat transfer between a body and its surrounding. Very, very simple. When you take courses in heat transfer, you're going to find much more complicated stuff. K will vary with temperature, okay? But at this point, it's a model, and it's appropriate sometimes. In this case, it's only a first-order differential equation. And again, let's get the physics and the math to agree, okay? In order to predict the time rate of change, in order to predict the time history of the temperature of this body that I just removed from the oven, obviously I'm going to need an initial condition. What's its temperature at time 0? Because the differential equation only relates the transfer of heat from it, right? And therefore, I need, just based upon my physical understanding, I have to know the temperature as soon as I take it out and introduce it into the new environment. So it's T at time equal to 0, it's initial value column. That's the only piece of data I need. It's a first-order differential equation. It makes perfect sense. Again, the physics and the math have to be in concert with each other. Okay? So that's Newton's law of cooling. Okay. Any questions on that? It's a very simple model, but it is. Okay, I'm not going to do everyone that's in the book. Let me give you one for fluid mechanics. Okay? This is interesting. This will be draining of a tank. Okay? So it's basically a fluid draining from a tank. defend your numbers, you have to say, well, here's my assumptions over here. You always have some assumptions, and those have to be fluid related. Okay, so what's the situation over here? Let's say for simplicity, I've got a cylindrical tank that we have to prove this out. This supposed to be a right circular cylinder. And we'll call this area up here, even though it's basically pi r squared, it doesn't have to be any type of cross section. Let's A sub W be the area of the wall, so many square feet. That's the area of the top and bottom portion of the cylinder. Okay? And this is going to be filled up with some fluid. Okay? Let's say fluid height is this. We'll call that H of T. Okay? Where H of T goes from the bottom, it's measured from the bottom up to the free surface. Okay? And now, there's going to be a small hole in the bottom of it. I'm sure very small hole here. And I'm going to exaggerate it, just throw it in red over there. Okay? And that thing is going to have an area A sub H, area of the hole. AH much smaller than AW for the little hole in the thing. Okay? What's going to happen basically? There'll be some fluid pressure, and obviously what's going to happen is that fluid is going to start dripping out of this thing. Right? You get like a little cylinder over there. Okay? And we want to find a differential equation that governs the height, H of T, of the fluid. Now, one of the assumptions over here that the book doesn't mention, okay, we're going to assume that the fluid is irrotational. That means anything to you, inviscid, okay, and incompressible. Okay? Incompressible basically means conservation of mass is conservation of volume. If you take courses in fluids, you'll talk about compressible fluids, okay, like air, sometimes compressible, but a lot of times not. You won't get a shock wave, okay, if you consider something to be incompressible. Okay, so consider a small interval of time, okay, and so let's have a little simplify. Yeah, I've got area of the hole,